In this lesson, we look at average rate of change. So we'll start the lesson off by looking at just rates of change, which is something that you should be familiar with from way back when. We're going to start by this function here, y equals, or f at x equals 2x plus 1. So we can represent this function using a table of values as I've done here, or using a graph, which I've done here. So if I asked you way back in grade 9 to find the rate of change, there are a couple ways that you might do that. The first one might be to look here and find the differences, what we would have called the first differences here. So -1 subtract -3 is 2, so we can see there's a difference of 2 here, and we can do that all the way along here. 5 minus 3 is also 2. And then we can also look here to find the differences here. -1 minus -2 gives us 1, and the same thing over here. So had I asked you to give me the rate of change here, you might have done this as looking at the rise or the change in y over the change in x. So you might say here the rate is equal to the change in y. So delta just means the change in, so the Greek letter delta and y, and then delta x is the change in x values. And we would say here the change in y, well, it's changing by 2 every time. And then the x's are changing by 1 every time. So we get a rate of 2 over 1, which is equal to 2. We can do the same thing on the graph over here. Choose any 2 points on that graph and find the change in y. I'll use these 2 points here because they're easy to see. And we can see here that the change in y goes from 1 to 3, so that's a change of 2. And then the change in x would be 1. Now, if you wanted to extend this a little bit, just a reminder, we could actually look anywhere. We could say, hey, what's the change in y all the way from here, from -3 to 5? Well, that will be 8. And the change from -2 to 2 is going to be 4. So the rate here would equal the change in y, which was 8, over the change in x, which is 4, for a total rate of 2. Now, we would have said before that the rate is the same thing as the slope. And we spent a lot of time talking about slope and y-intercept. So, and again, from the equation, we can see that the slope is right here. And we called this the y-intercept, where the graph crosses the y-axis. We're not really interested in the y-intercept today, but just a reminder there. So to find the rate of change, we divide the change in y by the change in x. That was the equation here, change in y divided by the change in x. So the rate of change in this case was equal to 2, and again, we may have written that before as m equals 2. So what I want you to do now is to think about, what does it mean to talk about a rate of change when we're talking about this function here, g of x equals x cubed. So I've created, again, a table for you and a graph to see what that looks like. And again, if you look at the table here, we can go ahead and try to find a rate from the table. The difference from -8 to 1, I guess that's going to be an increase of 7. From -1 to 0 is an increase of 1, and an increase of 1, and an increase of 7. Now you can see here that the first differences are not the same. And in fact, you would have looked at before with just a quadratic function, seeing that the first differences weren't the same, but the second differences were. And because this is a cubic function, it turns out the third differences are going to be the same. Anyway, that's just something to notice. Not really helpful here, because remember, we were talking about trying to find the rate of change, or the rate for this function. And you can see that it's different. The x values are changing by 1 every time, but the y values are changing by different amounts. And we can see that on the graph. You know, if we're trying to find the rate, let's say over here compared to over here, you can see that the graph is a lot steeper way out here than it is in here. So we need to find another way to find the rate of change for a function that's nonlinear. And that's really what the idea here behind the average rate of change is that what we're going to do is we're going to look at not the rate of change for the whole function, but we're going to look at the rate of change between any 2 points. So in order to find the average rate of change, what we're looking for is the slope of a line connecting 2 points. So I'm going to choose 2 points. It doesn't matter which 2 points we choose. I'll just choose two that are sort of easy to see here. We'll start with the origin here at 0, 0, and just so things are a little bit spread out, we can see what's going on. We'll use this point here, 2, 8. So those are 2 points. If I want to find the rate of change between those 2 points, what I'm really doing is I'm trying to find the slope of the line that connects those 2 points. So we kind of ignore what happens in the middle here and say, well, we know that we start here and we finish here. Let's just find the average rate of change. And you can kind of think about this as a drive. Let's say that you and I are both at the school. We want to drive to some destination. And let's say that I drive very slowly but at a very consistent rate. So let's say I drive the same speed the entire way. My graph might be represented here. And let's say that you drive really fast, really quickly, and then you make a stop. So in that case, your graph might look like this. You drive really fast, you make a stop, and then you continue to drive fast. We might end up at the starting and finishing at the same points at the same time, but clearly our rate of change or our speed wasn't the same, but our average speed was the same because we started and finished at the same time. So that's kind of what we're getting at here when we talk about average rate of change. So this line here that we drew is called a secant. So a secant is any line, secant is any line that connects 2 points on a function. So this green line here is a secant, and now that we have a line, we can find its slope the same way that we would have done before. So the average rate of change from x equals 0 to x equals 2, well, from here to here, we just need to find the slope of this line. Well, the y values are changing by 8, and the x values are changing by 2. So the average rate of change, and I just use ARC as a short form for average rate of change, equals the change in y over the change in x, which we saw here was 8 over 2. And so our average rate of change on this function gives us 4. So, and this works for any kind of function. No matter what function we're looking at, we can always find the average rate of change by drawing a secant and finding the slope of that secant. That'll give us the rate of change between any 2 points. Now, what we want to do is we want to take that idea. That's a really important idea, and it's important for you to remember that average rate of change is just the slope of the secant. But what we can do is we can actually find a function that represents the average rate of change, which is kind of an interesting idea and will be certainly helpful if you decide to move on and explore some calculus a little bit later on. So what I'm going to do is I'm going to label a few points here. We'll use those same points that we did before. We'll use 0, 0 and the point 2, 8, which is just at the very top of my graph, just so that things are really far spread out. But I'm going to make this very generic so that these could be any 2 points on any 2 function. So I'm going to call this point, I'm going to say that it has coordinates x for its x value, and I'm going to say that its y value is f at x. So no matter what the function is, we substitute the x value into the function and we get the corresponding y value. And that's going to be this ordered pair x comma f at x. Now, what I'm going to do here is going to seem a little bit odd to you, but we're going to go ahead and do it anyway. And what I'm going to do is I'm going to say that the distance, from that first point to our second point is h. So I'm going to call that's the difference between those 2 points, the distance between those 2 points. So whatever point we're talking about, again, I'm trying to make this as general as possible so that we can use it everywhere imaginable. So then the coordinate of the point up at the top here, it has an x coordinate of x plus h, because we were at x down here and then we added h to it, so this has to be x plus h over here. And then the y value of this point is whatever the function value evaluated at x plus h is. Well, that's just f at x plus h. So we sub in the x plus h into our function and we get our y value. So more generally now, if we want to find the average rate of change, it's the change in y over the change in x. Well, in order to find the change in y, we subtract these two y values. Well, we have a y value here, and we have a y value, over here. We want to subtract those two. So our average rate of change, generally speaking, is f at x plus h. That's our y value right here, minus the y value here. And then we want to divide that by the change in x. Now, the change in x is really just the difference between these two x values, this one and this one. We already know that that distant difference should be h, but let's go ahead and just show you why that is. So the x value here is x plus h, and we want to subtract the x value here, which is just x. And you can see now that the average rate of change is equal to f at x plus h minus f at x, all divided by, and we've got a positive x and a negative x here, so we're left with just an h in the denominator. This looks a little bit confusing, but this is a function that will work every single time we try to find the average rate of change. And as I said, it's a function. So if we're starting with a function, this will give us a function which allows us to find the average rate of change at any point along our original function. So to show you how this equation works, we're going to use this example here, f at x plus h, f at x being x squared. So we want to find the average rate of change. The average rate of change, well, that's just this right here. So let's start out with a little bit of information. We know already that the f at x part of that equation is going to be here. We should maybe talk a little bit about what does f at x plus h look like. Well, f at x plus h just means we're substituting an x plus h everywhere we see an x. So instead of x squared, we're going to have x plus h squared. So we now have f at x, we now have f at x plus h, we'll plug them into the equation. So I'm going to just write this out again, just for practice. The average rate of change is f at x plus h minus f at x, and that's all over h. And let's substitute in. So we already said f at x plus h, maybe we should use some color here. F at x plus h is here, so this part of the equation is just going to be this x plus h all squared. So we get x plus h squared, and then we have to subtract f at x. Well, f at x was right here. F at x is just x squared. So from this, we're going to subtract x squared. And then we divide by h. Oh, sorry, I lost my minus sign there. So we can do a little bit of algebra now, simplify this. Remember that x plus h squared, I know there's a temptation to just say that's x squared plus h squared, but remember that x plus h squared is really x plus h times x plus h. And if we expand this all out, we'll get an x squared term, we'll get an xh term, another xh term, and then another h squared term. I shouldn't say another, that's our first one. So if we simplify this, we get x squared plus 2xh plus h squared. All right, so the shortcut here, some of you may know this already, but when you square a binomial, we basically square the first term, which we did here. We double the product, so the product is x times h, and we double that, so we get 2 times x times h, which is here, and then we square the last term. So square the first term, double the product, and then square the last term will give you the answer. If you don't like that, you can certainly do it the long way. All right, so let's go back here. We know that x plus h squared now is x squared plus 2xh plus h squared, and then we have to subtract our x squared, that is right up here, and we're dividing all of that by h. So this looks a little bit nasty. Let's simplify it a little bit. We have an x squared term over here and a negative x squared term over here, so we can go ahead and add those and get nothing. And now one of the interesting things that you'll note is that both of the terms left have h's in them. Let's go ahead and factor that h out. And I know we could factor, not always, but in some cases we'll be able to factor more than that. Really what we want to do is just factor out the h so that we can get rid of the h in the denominator. So I'm going to continue this up here, and I'll just factor out the h. That's going to leave me with 2x plus h and then we have an h in the denominator. Again, we can divide out the h's from the numerator and the denominator, and we get that the average rate of change here is equal to 2x plus h. That is our general expression, or the general function, for the average rate of change. What this means is that now we can find the average rate of change between any 2 points just knowing the x value that we want to start at and the h value, the difference between the two x values. We'll do an example of that so you can see what that looks like. So, find the average rate of change from x equals 1 to x equals 3. Just a reminder, we had the expression here. I should have written it on the top. The average rate of change here was equal to 2x plus h. So some of you might be wondering, which x value do we substitute into this equation? And the answer here is that it doesn't really matter. I typically substitute the smaller x value in, and then my h value is always positive. If you substitute a larger value in, if we substitute x equals 3 into here, we just need to make sure that h is negative because we want to go from 3 to 1, which means we need to subtract 2. So I'm going to say here that in my function, my average rate of change function, that x is equal to 1, and h is the difference between those two x values, which is 3 minus 1, which is equal to 2. So now I have the two things that I'm going to substitute into my formula. So the average rate of change from x equals 1 to x equals 3 is equal to 2 times x, which is 1, plus h, which is 3. 2 times 1 is 2, plus 3 more is 5. So the average rate of change from x equals 1 to x equals 3 is equal to 5. All right, let's move on to a harder example, a little bit harder. It's not a lot harder, but it is a little bit harder. Sorry, before we do that, I should mention that, the next step in this, and I want you to do some thinking about this, is what if I ask you to find the average rate of change for the function f at x equals, let's say, 2x squared plus 1. What does that look like? Well, we do, and I won't do it. I'll leave it as an exercise for you to do, but again, we do the same sort of thing as if we're trying to find the average rate of change for this function. We need to know what f at x plus h is. So that means substitute an x plus h into the function everywhere we see an x. So over here, we're going to have an x plus h. So 2 times x plus h squared plus 1 more. That's our f at x plus h. Our f at x is already right here. So now we can go ahead and do our average rate of change equals f at x plus h, which we said was this thing right here, minus f at x, which is 2x squared plus 1. Now be careful here. I'm going to suggest you put some brackets around all of this because we're subtracting all of it. Otherwise, you don't distribute that negative sign properly. So just be aware of that. And don't forget we need to divide this all by h. I said I wasn't going to do this, but there's the bulk of it done. The next step is to expand, collect like terms, simplify, and factor just like we did on the rest. See if you can do that one, and then we can move on to this next one. I wanted to show you this one because it looks a little more daunting. It doesn't at first, the only difference here is the fact that this is a 3 instead of a 2, but it gets a little bit tedious, and I want to show you how tedious it gets. If you've taken data management and you've looked at the binomial theorem, that'll be helpful. If not to worry, we'll get there eventually. So we were trying to find the average rate of change here. So the average rate of change is f at x plus h minus f at x, and all of that gets divided by h. So I'm going to start over here by writing down what is f at x plus h. Well, f at x plus h just means substitute an x plus h everywhere we see an x in the function. So this becomes x plus h cubed. All right, let's go to it. Looks easy so far, right? Yeah. Hang on, we're getting there. So f at x plus h, we already said, is here. So we're going to write this over here. We get x plus h cubed minus f at x, which we said was x cubed, all divided by h. Easy so far, right? Now here's just where things get a little bit tricky. remember that x plus h cubed does not equal x cubed plus h cubed. X plus h cubed is x plus h times x plus h times x plus h. So that's where things get a little bit messy. And if you do this all out, so you might want to take, everything in the second set of brackets, multiply it by everything in the third. It doesn't matter what order you do it in. And then take whatever you get for that answer, take the x plus h here and multiply it by everything there. It turns out you're going to get x cubed plus 3x squared h plus 3x h squared plus h cubed. So that's the hard part here. And again, it's not so much that it's hard as tedious is doing the expansion here. And perhaps a little bit later on, we'll talk about a shortcut here that might help you out a little bit. So this is x cubed plus 3x squared h plus 3x h squared plus h cubed. Ooh. So that's our f at x plus h. And then don't forget we need to do this part right here, minus f at x. So minus f at x was just x cubed. Divide that by h. And one of the things that you should notice when you're doing this is that the all of the terms that don't have an h in them should disappear. We're subtracting an x cubed here, and we had an x cubed over here. Those are the only two terms that don't have an h in them. And the reason for that is that we should be able to factor an h out of what's left. And if we can't, we've probably made a mistake somewhere. So I know for sure that x cubed minus x cubed is nothing. We're left with all the other terms have an h in them, so let's factor that out. And we get 3x squared plus 3xh plus h squared. And all of that's over h. And again, the whole purpose for factoring out those h's in the numerator was so that we could divide them out here in the denominator. And so we get that the average rate of change, I'll just slide this over here, kind of ran out of room. So the average rate of change is equal to 3x squared plus 3xh plus h squared. So again, anywhere on this function, the average rate of change is equal to this right here. And again, x is any point, and h is the distance from that point to another point. So when we're asked to find the average rate of change from x equals negative 2 to 4, remember this function kind of looked like this. X equals negative 2 all the way to 4. We're trying to find the slope of the line, or the slope of the secant that connects those 2 points. Oh, sorry, that was a really bad drawing of a line, but hopefully you get the idea. So the straight line that connects those 2 points. I think I'm going to end up erasing, most of this. Let's try that again. Hopefully you get the idea, though. So we had our function. It looks something like this. And we want to go from x equals negative 2. Sorry, I drew in a little bit more of a bump in there than I should have right in here. But so we want to find the line that connects those 2 points, the slope of the line. And again, we have our function. That's what this tells us right here. The average rate of change function tells us what that is. So again, I like to start with my x value as being the smallest x value. If you prefer to start with the biggest, that's fine. Just make sure that you make your h the opposite sign of mine. So again, h is the difference between these two x values. So I'm going to take the larger one and subtract the smaller one. 4 minus negative 2. Well, that's going to give me 6. And I plug those into here. So the average rate of, when I say here, I mean into here, sorry. So the average rate of change is equal to 3 times x squared. So my x is negative 2 squared plus 3 times negative 2 times h, which is 6, plus h squared. H squared is 36. Well, I could just write that as 6 squared to start, I suppose, so you can see where it came from. Let's try that again. Sorry, I lost my train of thought there for a second. All right, so that's a 6 squared. And then we could just work this out. Negative 2 squared, don't forget your order of operations. Negative 2 squared is 4. 4 times 3 is 12. And then here we're going to have negative 2 times 6 is negative 12 times 3 is going to be negative 36. And over here we'll have a positive 36. Oh, isn't that nice? Negative 36 and a positive 36. That gives us an average rate of change of 12. So the average rate of change from here to here, or the slope of this secant from here to here, or the slope of this secant, is equal to 12. That's how we can find the average rate of change. That's how we can use it to find the slope between any points. So you might say, again, why didn't we just find the slope of that line? But now I can ask you, what's the slope between x equals 7 and 14? We don't have to go through and find the y values. We can just plug in the x and the h values here.